Hello class, this is section 4.3, logarithms. So let's jump right into it. Express this equation in exponential form. Well, let's do that. The way I like to do this, I like to cross out the word log and then swap these two numbers. So 3 is your base, and then when you swap 27 and 3, the 3 becomes the exponent, and then the 27 goes on the other side of the equal sign, and you drop the word log. So there you have it. That's exponential form. And you want to make sure that it makes sense. 3 to the third does equal 27, so you know you're doing it right if the equation is true. All right, for the next one, same thing. Cross out the word log, swap these two numbers. The base is 3, the exponent is 0, and the number on the other side is 1. And that is also a true statement. Okay, let's try the next problem. This time we're going in the opposite direction, so the same thing holds true. All you got to do this time is write the word log. Your base is the same base as the exponential power base here, which is 3. And we switch these two numbers, the exponent, the 3 in the exponent, and the 27 gets swapped. So the 27 comes to the left, and the 3 goes to the right of the equal sign. Same thing here. The base is 10, and we switch these two numbers. So you can write 1 over 100 in parentheses and a -2 on the opposite side. All right, let's move on to the next problem. When it comes to evaluating, I always like to write equal to x, but that's just an optional thing. And then we do what we did before, which is convert this to exponential form, which means cross out the word log, swap these two numbers. So the base is 3, the exponent is now x, and that is equal to 3. And this one, you can pretty much solve this in your head. 3 to the what power gives you 3? Well, it has to be 1, because 3 to the 1 is 3. All right, this one, same thing. I like to set it equal to x, cross out the word log, swap those two numbers. The base is 3, the exponent is x, and that's equal to 1. Well, any base to the 0 power is always 1, so this has to be 0 in order for it to be true. The next one, same thing, equal to x, swap these two. So base is 6, exponent is x, and that is equal to 6 to the 5th power. And whenever you have the bases the same, that means you can set the exponents equal to each other, so x equals 5. All right, moving on. So same thing. So once again, I always like to write this equal to x, cross the word log out, swap those two numbers, so I get 3 to the x power is equal to 1 over 243. Well, in this case, I want to get the bases to be the same on both sides. So I'm going to go with base 3 because it's easier that way. So let's convert this to base 3. Well, let's figure out what number to the 3 to the what number gives you 243. I believe it's going to be, probably 5. Yes, 3 to the 5th power gives you 243. However, it's in the denominator, which means we have to make the exponent a negative. So it'd have to be 3 to the -5. And you can verify that. If you do 3 to the +5, you get 243. But in order to turn it into the reciprocal, you would have to include the negative because of this this rule for exponents. So if you have a negative exponent, that means you take the reciprocal. And so that's why I put a negative in front of the 5 so that I can turn that into 1 over 243. And then the one-to-one property for exponential functions says that if the bases are the same, then the exponents must equal each other. So x must equal -5. Okay, this one's similar. That is going to be, swap those two numbers. So you're going to have 2 to the x power equals radical 2. Well, we know that the square root means it means 2 to the 1/2 power. Because of this rule here, This is another rule for an exponent. Whenever you have a radical and the index is n, then that converts to 1 over n as a rational exponent. So x equals 1/2. And finally, the last one, same thing. Swap base 5, exponent x equals 0.2. Well, this might be a little bit difficult to see as a decimal, but if you convert this decimal to a fraction, you'll get 2 over 10. All right, and then you simplify that fraction, that becomes 1/5. And then we know that 1/5 is the same as 5 to the negative 1. And now you see you have the bases the same, which means the exponents must also equal each other. So x equals -1. Okay, let's look at this one. So this time they already have the equal sign for us. And so let's convert this to exponential form by crossing out the word log and swapping these two numbers. The base is x this time. The exponent is 4, and that equals to 256. 256. In order to solve for x, you have to take the fourth root of both sides. That'll cancel that out. So x is going to equal the fourth root of 256, which is 4. You can verify that. 4 to the fourth power should equal 256. All right, let's do the same thing here. Cross out the word log, swap. Base x, exponent 3/2 is equal to 512. In order to get rid of the 3/2 exponent, we raise it to the 2/3 power. That'll cancel out the exponent, and now we're left with x is equal to the 512 to the 2/3 power. That means you need to take the cube root of 512 first, and then you want to square that. That's what that means. So the denominator is the index of the radical, and the numerator is the exponent that you want to raise that to. So on your calculator, if you do the cube root of 512, you should get 8. And so that's going to be 8 to the second power, which is 64. All right, this one says use a calculator to evaluate the expression. Correct to 4 decimal places. So all I got to do is simply type in log 7, close parentheses. I'm getting 0.845, and since I have a 0 and a 9, I need to round that up to 1. So 0.8451. Next one, log 40.8. I'm getting 1.61066, which rounds to 7. Okay, this last problem says graph the function not by plotting points, but by starting from the graphs in the figures below. So they want us to do transformation. So first, we want to locate the parent function. The parent function would be, in this case, log base 5 of x, because that's what the base is here. So this is the parent function. So if we locate that one, that would be this blue one here. And if you recall from, I forget what section, but that -3 means that you're going to shift 3 units to the right. Shift 3 units right. So there is an asymptote right on the y-axis. X equal to 0 is our asymptote. But since we're shifting 3 units to the right, the asymptote is also going to shift 3 units to the right. So it's going to go 1, 2, 3. So our new asymptote would be right at 3. And so our graph would look like, notice that all of these graphs go through point 1, 0. But since everything's shifted, that means they're going to go through 4, 0. So it'll look something like that. So I'm just going to draw it right on there. So here we go. X equals 3 is 1, 2, 3. That's our asymptote, our new asymptote. And the point is now going to go through 4 instead of 3. Instead of 1. And then the graph is just going to look like that. All right, so the domain is going to be, so I'm just going to label this f of x equals log base 5 of x minus 3. The arrow just indicates that it continues indefinitely in that direction. So the domain starts at 3 and goes towards infinity. So it's going to be 0, infinity. Notice I put open parentheses because it doesn't touch the asymptote. It just gets infinitely closer and closer to it, but it never touches. And this graph goes infinitely downward and infinitely upward. So it's going to be all real numbers for the range. And the asymptote we stated was right at 3, x equals 3, because it was at 0, but since things got shifted 3 units to the right, it now is x equals to 3. And that concludes this